Imagine that planets do not form naturally, but are sown like seeds. For a long time, scientists puzzled over how gas giants form so quickly around distant stars until an object named Tri-A Atlas appeared, drifting from the void with a chemical composition that resembled a cosmic instruction. This interstellar traveler contains the precise materials needed to begin planet formation, as if it were created for this purpose. But aboard this celestial seed, there is something else that even skeptical astronomers ponder. Could there be something alive inside? The evidence we have gathered points to three possibilities, each more unusual than the last. From sleeping microbes to living technologies, the truth about Tri-A Atlas will change our understanding of humanity's place in the galaxy. At the end of this night expedition, you will understand why this strange object may hold the key to our understanding of the cosmos. Is Tri-A Atlas really alive? Could there be life within Tri-A Atlas, or is it just a seed of a planet? Before us are three paths, like trails through an alien forest. The first is an ordinary comet with unusual chemistry that defies our expectations. The second is an artificial artifact, carefully disguised as space debris. The third is a biological or living seed containing blueprints of yet unborn worlds. We will test each of these hypotheses based on accumulating evidence and will follow the data, even if it challenges everything we thought about planet formation. Let's quickly establish the basics. 3I Atlas, the third confirmed interstellar object ever discovered by humanity. The Atlas team in Rio Hurtado, Chile, discovered it on July 1, 2025. This traveler moves along a hyperbolic trajectory, defying the gravitational pull of our sun, confirming its interstellar origin. Fortunately for the inhabitants of Earth, it poses no threat. Its closest approach is about 1.8 astronomical units from our planet, which will occur on December 19, 2025. However, here lies our first intriguing clue. The timeline itself resembles a carefully choreographed cosmic dance. October 3, 2025, marks its close pass by Mars at a distance of about 30 million kilometers. On October 29th, he reaches perihelion, the closest approach to the Sun at a distance of 1/3600th of an astronomical unit, conveniently located behind the Sun from the Earth's perspective. On March 16, 2026, a grand finale will occur, a close encounter at a distance of just 3600ths of an astronomical unit. These checkpoints open unprecedented opportunities for observation for several spacecraft. Orbital Mars probes are ready, and the potential resources of the Jupiter system await their moment. The cosmic clock seems almost too perfect, too convenient, a thought that will arise again as we investigate. Now let's turn our attention to the growing anomalies that do not fit our classification of comets. A gas coma appears, dominated by carbon dioxide, whereas water vapor usually prevails in such phenomena. Early hydroxyl activities, a sign of water dissociation, are found far from the warm embrace of the Sun, challenging conventional notions of comet awakening. A dust trail directed towards the Sun creates what some call forward illumination, defying expectations of space debris behavior. It is particularly intriguing that spectroscopic analysis reveals traces of nickel, while the lines of iron remain disappointingly weak or completely undetected. The behavior of polarized light tells its strange story, not matching the signatures of familiar comets in the solar system. Each anomaly itself provokes curiosity. Together they form a pattern that demands explanation. This is not just another comet drifting in our cosmic neighborhood. If this is a natural object, then the three-eyed atlas reinterprets our understanding of how and where comets form in the icy expanses between stars. If it represents a seed of a planet ready to be captured by a young star system, then it changes the timelines of planet formation. If this is an artificial object, created or intentionally sent, then we stand on the brink of the most significant discovery in history. We promise to conduct a fair test, separating measured facts from clearly defined speculation. The scientific community expresses deep skepticism towards extraordinary claims, and this is justified. Expert criticism will be considered alongside anomalous observations. Understanding what interstellar means requires awareness of the physics of cosmic wanderers. These objects move at high speeds relative to local stellar motion, following hyperbolic trajectories with eccentricities significantly greater than 1. Most interstellar visitors pass through our solar system unnoticed, only detected after they have already left it, if they are detected at all. The early discovery of the three-eyed atlas changes everything. Months of coordinated observational campaigns are unfolding around the world using humanity's greatest tools: the Hubble Space Telescope, the James Webb Space Telescope, ground-based observatories across the globe, and resources stationed in our solar system. Never before have we had such comprehensive surveillance of an interstellar intruder. If the three-eyed atlas represents a seed, a cosmic gardening tool evolved in nature, or created by intelligence, what can it sprout? Can seeds contain chemical ingredients for life? Can they carry the very life of sleeping passengers waiting for resurrection in the warm embrace of a young star system? The consequences of this research span multiple disciplines. Biology meets astronomy. Planetary science confronts questions of design and intent. The search for extraterrestrial intelligence suddenly faces the need to study not radio signals from distant civilizations, but a possible artifact drifting right under our noses. As a result of this investigation, three likely conclusions will emerge based on the collected data. You, the jurors, will weigh the testimonies and choose the explanation that best fits the facts. Will you conclude that only nature created this interstellar wanderer? Will you accept the radical idea of cosmic seeding, whether of natural or artificial origin? Or will you encounter the astonishing possibility that intelligence has come to us, hiding under the guise of a simple comet? Time relentlessly moves towards our first major observational phase. Mars awaits its close contact in just a few weeks. The perihelion approaches the sun, like a curtain on a stage where the real play can finally begin. Evidence accumulates, theories compete, and somewhere in the darkness between the stars, other wanderers sail towards fateful meetings we cannot yet imagine. But first of all, we need to consider the loudest argument, which resonates both in scientific circles and on social media. A hypothesis that refuses to whisper when it could shout about its existence, challenging traditional wisdom. Part 2. The hypothesis of aliens comes not with quiet whispers, but with confident statements from Abraham Loeb of Harvard, a respected astrophysicist whose previous work on black holes and cosmic structure deserves academic respect. Nevertheless, his interpretation of the Tri-A Atlas sparked heated debates in the scientific community. Loeb presents his viewpoint with mathematical precision. He emphasizes the extraordinarily tight alignment of the object with the planetary plane of our solar system. Moving counterclockwise, yes, but tilted only about 5 degrees from the ecliptic. Most interstellar guests arrive from random directions, their trajectory reflecting the chaotic dynamics of stellar encounters. 3 Atlas appears almost domesticated, as if following familiar orbital highways, with consecutive encounters with planets particularly troubling Loeb. First Mars, then Venus at a greater distance, then the remote vicinity of Earth, and finally the threshold of Jupiter. A cosmic route that looks like a reconnaissance mission crafted by a patient mind. He calculates the probability of such alignment happening purely by chance to be about 0.5 thousandths of a percent based on his assumptions. This is his interpretation, not a consensus among colleagues, but the mathematical foundation requires serious consideration. The phenomenon of glowing ahead serves as the second pillar of evidence for Loeb. It highlights the sun-oriented, cigar-shaped profile of the object's brightness, the illumination of which raises his deep suspicion. However, the analysis conducted with the Hubble telescope reveals a more nuanced picture. Solar dust caused by heating is accompanied by a faint anti-solar tail directed in the opposite direction. The physics of comets can indeed create brightness directed towards the sun through asymmetric ejection of gases and dust. Here we need to separate peer-reviewed observations from speculative interpretations. Brightness directed towards the sun exists. Many telescopes confirm this reality. Whether it represents natural physics or artificial design remains a hot topic of debate. The story of nickel detection becomes increasingly complex upon closer examination. Very large ultraviolet and visible telescopes, as well as spectrographs, detected radiation lines of neutral nickel, while signatures of iron were absent in these spectra. Loeb and his colleagues suggest that such a picture may indicate recycled metals, alloys produced from industrial processes, rather than cosmic chemistry. However, the absence of detection does not imply a zero concentration. Iron may be below detection thresholds, or excitation conditions may favor the emission of nickel instead of iron. Previously, comets displayed signatures of nickel without raising questions about extraterrestrial production. The transition from unusual metal ratios to industrial origins requires outstanding justification. Loeb delves into darker assumptions using his dark forest concept, borrowed from science fiction but applied to real astronomical data. If 31 Atlas represents a reconnaissance probe, then planning the perihelion passage behind the Sun would minimize observation opportunities from Earth. From our perspective, time appears conveniently opaque. This interpretation suggests intentional design, deliberate concealment, and strategic thinking applied to orbital mechanics. Current data shows no evidence of course correction or maneuvering, but Loeb claims advanced technologies may operate below our detection thresholds. Loeb's publications and his colleague Hibberton Crowell explore scenarios ranging from passive observation to possible hostile intentions, contemplating the capabilities of a probe, data collection goals, and even potential threats to human civilization. The scientific community responded with harsh criticism, calling such assumptions nonsense and baseless intimidation. This backlash reflects deep disagreements within astronomy. How far should scientists venture into speculative areas? When does healthy skepticism become closed orthodoxy? When does open inquiry turn into irresponsible sensationalism? True technosignatures will require specific observational criteria. Constant non-gravitational accelerations incompatible with sublimation physics would trigger immediate alarm signals. Artificial light curves, brightness changes tracking programmed rather than rotational patterns could indicate active systems. Structured repetitive bursts may indicate positional control or deliberate signaling. Narrowband radio waves or optical emissions would scream artificial origin to any astronomer. So far, none of these clues have been found in the data. 31. Atlas behaves quite similarly to a comet, albeit an unusual one, by all measurable parameters. It emits gas, forms a comet, demonstrates dust emission patterns corresponding to solar heating, and strictly follows the laws of gravity. The hypothesis of extraterrestrial origin faces the greatest challenge, the burden of extraordinary evidence. Carl Sagan's famous aphorism is more relevant than ever. Extraordinary claims require extraordinary evidence. Lioba's mathematical arguments about the probabilities of trajectories, while interesting, do not prove artificial origin. Statistical improbability alone cannot distinguish design from natural coincidence, especially in the case of unique events rather than reproducible patterns. The broad scientific community remains deeply skeptical, and their caution serves important functions. False claims about the existence of extraterrestrial technology would undermine public trust in astronomy and the search for extraterrestrial life for decades. The community learned harsh lessons from the premature excitement surrounding pulsars, fast radio bursts, and other phenomena that initially seemed impossibly artificial. But Lioba's persistence led to valuable scientific research. His hypothesis, although controversial, became a stimulus for active observational campaigns that contributed to the development of new analytical techniques and compelled the community to clearly articulate what evidence could confirm artificial origin. Even incorrect hypotheses can advance knowledge, refining our research tools. The interpretation of extraterrestrial origins also highlights our profound ignorance about interstellar object populations. We have only observed 3 confirmed examples. 1. I-Os Borisov. 2. I. Atlas. Broad conclusions based on such a tiny sample are fraught with errors. What seems anomalous today may become commonplace tomorrow as our capabilities expand, and the philosophical implications become more important than technical disputes. If the artificial origin is confirmed, I or Atlas will instantly become the most significant discovery in human history. Every assumption about our cosmic isolation will collapse. Every strategy for searching for extraterrestrial life will require a fundamental overhaul. Every planet protection protocol will face the urgent need for updates, but confirmation remains elusive, frustratingly unattainable, despite months of intense observation. Evidence consistently points to a natural origin, even if the specific chemistry and physics are more exotic than typical comets in the solar system. Moving forward, the hypothesis of extraterrestrial origin serves as an important guide for evaluating all observations. Every anomaly is analyzed through this lens. Each new dataset is checked for potential technotraces. The hypothesis may ultimately prove incorrect, which most scientists expect, but its failure will be based on factual data rather than rejection. Next, we must consider what the measured patterns of activity actually reveal about I, Atlas. The behavior of the object tells a story, but which story depends on how we interpret the increasingly complex evidence coming from our telescopes and spacecraft. Part 3. evidence of activity. The ultraviolet telescope of the Swift Observatory, split into optical, provided the first shock to traditional notions of comets. The emission of hydroxyl, a clear sign of water vapor dissociation, was recorded at a distance of about 3.5 astronomical units from the Sun. This distance significantly exceeds the traditional active zone where solar heat usually awakens cometary volatiles. To appreciate the significance of this anomaly, it is worth noting that most comets in the solar system remain inactive until they approach about 3 astronomical units. Comet Tri. I-Atlas began to emit water long before reaching this threshold, which may indicate an unusual composition or exotic sublimation physics. The early activity of the water hints at a porous, volatile-rich internal composition that reacts even to slight solar warmth. The near-infrared spectrograph team of the James Webb Telescope made an even more shocking discovery. Their analysis showed a carbon dioxide to water ratio of about 8:1, sharply skewed towards carbon dioxide compared to typical comets in the solar system. This composition profile places Tri-I-Atlas in an unexplored chemical domain. Most known comets show a predominance of water, where carbon dioxide plays a secondary role. The opposite ratio indicates formation in conditions much colder and richer in carbon dioxide than the regions from which our solar system's comets originated. Perhaps Tri and Atlas formed at the distant borders of another star system, where carbon dioxide could freeze preferentially compared to water ice. Alternatively, unusual chemistry might reflect thermal processing during interstellar travel. Bombardment by cosmic rays and encounters with stars can alter the surface composition on geological timescales. The specific mechanisms remain unclear, but the chemical signature definitely distinguishes Tri-I and Atlas as chemically different from local comets. The emission lines of cyanogen reinforce the interpretation of the comet as active, adding another detail to the chemical inventory. CN emission typically correlates with the sublimation of organic compounds, suggesting that Tri-I-Atlas contains complex carbon-nitrogen chemistry in its core. This discovery helps astronomers determine chemical boundaries as an object approaches the Sun, providing important constraints on sublimation physics. Polar imaging measurements reveal perhaps the most intriguing anomaly ever detected. Initial observations show an unusually strong and extended negative polarization branch, with light scattering that noticeably differs from most comets in the solar system. This optical behavior suggests the presence of dust particles with exotic properties, unusual size distributions, levels of porosity, or compositional differences that affect the interaction of sunlight with the coma. Polarimetry serves as a sensitive tool for studying the physics of dust. The way particles scatter light closely depends on their size, shape, composition, and internal structure. Tri and Atlas produce polarization signatures that do not fit any clear category in our existing taxonomy of comets, suggesting formation processes or evolutionary histories unlike anything we have seen before. The Hubble Space Telescope resolved the mystery of the foreground glow with characteristic precision. High-resolution images show a dust plume emanating from the sunlit side, caused by asymmetric heating and gas emissions. Moreover, a faint tail stretches in the anti-solar direction, which fully corresponds to the expected behavior of comets. This observation refutes some more exotic interpretations of the front brightness. The heat from the sun naturally creates temperature gradients on rotating bodies, leading to the preferential release of gases from warmer surfaces. The received dust patterns can indeed create brightness directed forward, without the need for artificial explanations. Hubble's size limitations impose important constraints on speculations. The core diameter is estimated to be between 0.44 and 5.6 kilometers, which is completely different from the sizes actively discussed in earlier materials. This relatively modest scale excludes certain categories of exotic hypotheses, while conveniently fitting within the expected parameters for interstellar travelers. It is difficult to measure exact sizes when active comets overshadow the core signal. The Hubble's resolution is reaching its limits, even with careful image processing and multiple observational epochs. Current size estimates have significant uncertainties but set reasonable boundaries for theoretical modeling and comparison with other interstellar objects. The cumulative pattern of activity in the foundations resembles the behavior of comets, while demonstrating chemical and physical anomalies that distinguish Tri-I-Atlas from typical examples of the solar system. This combination of familiar physics with exotic composition creates interpretative difficulties for astronomers trying to classify the object. What observational evidence could unequivocally separate natural origins from artificial ones? Constant accelerations, akin to thrust, incompatible with sublimation models, would immediately provoke artificial hypotheses. Such accelerations could manifest as systematic deviations from purely gravitational trajectories, potentially observable through precise astrometric monitoring over long periods. Special spectral features represent another potential clue. Narrow bands of radiation at frequencies linked to specific technologies or elemental ratios, which cannot be achieved naturally, will require artificial explanations. However, defining impossible relationships requires a deep understanding of interstellar chemistry, knowledge that we currently lack. Temporal patterns in gas emissions may reveal artificial control systems. Natural sublimation follows predictable cycles related to temperature fluctuations caused by solar heating and periods of rotation. Artificial jets can demonstrate temporal patterns unrelated to natural rhythms, indicating active control of unstable release mechanisms. However, no such explicit signs have yet been identified in the data. The three-eyed Atlas comet still behaves like a chemically unusual but generally natural comet. Its anomalies and triggers raise doubts but do not refute traditional interpretations. The lack of clear techno-symptoms does not completely rule out artificial hypotheses. Perhaps advanced technology operates below the threshold of current detection methods, or we lack the conceptual frameworks to recognize truly extraterrestrial engineering. Nonetheless, the burden of proof remains on unusual claims, requiring appropriate evidence. Chemical anomalies raise profound questions about the diversity and formation processes of interstellar objects. If the three-eyed Atlas represents a typical chemical structure of an interstellar comet, our theories about the development of volatile substances in the outer part of the solar system require serious revision. The dominance of carbon dioxide and early water activity indicate formation conditions significantly different from those in the regions where comets in our solar system form. These chemical differences may be related to the history of the parent star system's formation, its subsequent development, and ejection mechanisms. Different stars form from molecular clouds with varying compositions. Different planetary systems undergo unique dynamic histories. The specific combination of factors that led to the formation and eruption of the three-eyed Atlas may be rare, or, conversely, common. We simply do not have enough data to assess this. As our research continues, evidence of activity provides important constraints for theoretical models and raises new questions about cosmic chemistry and physics. The object clearly belongs to the category of active comets, but this classification is expanding in unexpected directions. What can alive inside mean for such an object? This question requires careful definition before we can assess its plausibility against the accumulating evidence. When we speak of the three-eyed Atlas being alive inside, we must carefully navigate three different conceptual realms, each representing a different interpretation of what life might mean in the context of an interstellar wanderer. The first concept implies literal biology, microbial life forms existing in the core of an object, protected by layers of ice and dust from the harsh radiation background of interstellar space. This scenario requires organisms to survive not only in low temperatures but also under bombardment by cosmic rays, in vacuum conditions, and potentially for millions of years in a dormant state. Earth provides enticing examples of such resilience. Extremophilic bacteria successfully survive in conditions previously thought impossible for life, such as deep-sea thermal springs, highly radioactive environments, lakes beneath Antarctic ice, and even in the low Earth orbit vacuum. Some species can enter cryptobiotic states, remaining in suspended animation for decades or even longer, and then resume normal biological activity when conditions become more favorable. The protection provided by layers of ice and dust can theoretically shield internal microorganisms from lethal doses of radiation. Calculations show that several meters of frozen material can reduce cosmic ray exposure to levels acceptable for life. In warmer periods near the stars, heating could potentially create temporary zones with liquid water inside porous material, awakening dormant biology for short active periods. This biological scenario remains purely speculative as it lacks direct observational evidence. Nevertheless, the physics of this process seems somewhat plausible under carefully constrained conditions. The main questions concern the mechanisms of initial pollution, the timescales of survival, and the possibilities of detection. The second interpretation considers biotechnology, self-repairing materials, or systems that blur the boundaries between living organisms and artificial devices. The concept of living technologies draws inspiration from emerging fields such as synthetic biology and programmable materials. Imagine materials that respond to environmental changes, automatically repair damage, or alter their properties according to set goals. Such systems may include biological components in technological structures, creating hybrids that exhibit behavior similar to the living, without strict adherence to traditional biological criteria. In relation to the object Tri-Eye Atlas, this interpretation may explain seemingly intentional patterns of gas emission or adaptive responses to solar heating. This object could theoretically contain self-regulating systems designed to optimize performance in various environmental conditions encountered during interstellar travel. However, again, there is no observational evidence for such exotic explanations. The concept remains speculative, although the development of terrestrial biotechnology makes such possibilities increasingly real for sufficiently advanced civilizations. The third idea concerns complete artificiality, a spacecraft or probes deliberately disguised as a natural comet. This scenario requires complex engineering capable of mimicking a comet's behavior, concealing technological signs from astronomical observations. Creating a convincing comet disguise will demand a deep understanding of sublimation physics, dust formation mechanisms, and spectroscopic signals. Camouflage must function at various wavelengths and using different observation methods while maintaining the illusion of natural behavior. Such deception can serve intelligence purposes, allowing for detailed study of star systems without provoking defensive reactions from potentially hostile civilizations. The dark forest hypothesis suggests that cosmic survival may depend on remaining unnoticed by more advanced species. The detection of nickel without corresponding iron signatures has sparked particular speculation in this direction. Some researchers wonder if the ratios of metals indicate industrial processing rather than natural cosmic chemistry. However, the absence of iron lines in certain spectral observations does not prove a zero concentration of iron. The conditions of excitation, the ratios of abundances, and detection sensitivity influence which elements are noticeable in the spectra. Nickel emission was observed in previous comets, indicating no artificial origin. The transition from unusual metal ratios to industrial processing requires much more convincing evidence than what is currently available. A dusty cloud forming upon collision with the sun may have natural explanations related to asymmetric heating and rotational effects. Solar radiation creates temperature gradients on the surfaces of objects, causing preferential degassing from warmer areas. As a result, the dust patterns can create brightness directed forward, which may seem artificial to random observers. Regarding habitability in a three-eyed system, the physical conditions pose serious challenges for biological activity. Internal temperatures likely remain significantly below zero for most of their trajectory. Brief warming during encounters with stars may create temporary liquid zones, but they will only last for a relatively short time. A more plausible scenario involves organic chemistry processes rather than thriving ecosystems. Complex carbon compounds may slowly undergo transformational reactions during long periods of dormancy, potentially creating chemical conditions favorable for life if and when liquid water becomes available. The concept of living technology raises intriguing questions about the boundaries between life and artifact. If we discovered materials that grow, reproduce, adapt, and respond to environmental challenges, would we classify them as biological or technological? This distinction may prove insignificant for sufficiently advanced engineering approaches. Programmable materials represent one area of terrestrial research that could ultimately blur these boundaries. Materials designed for self-regulation according to specified instructions can exhibit behavior indistinguishable from biological growth or adaptation. When applied to interstellar research, such capabilities could provide remarkable versatility. Probes can adapt their configurations for different phases of emission, automatically repair damage, or change their behavior based on detected conditions in target systems. The burden of proof for any hypothesis about the existence of life inside remains extremely high. Claims about biology, biotechnology, or complex artificiality require evidence that current observations cannot provide. Speculations play a valuable role in expanding conceptual horizons, prompting new observational strategies and exploring theoretical possibilities. But they alone cannot establish truth. What specific evidence could support biological hypotheses? Detected metabolic byproducts, complex organic signatures incompatible with abiotic chemistry, or isotopic ratios indicating biological processing may provide compelling clues. Nevertheless, distinguishing between biological and abiotic organic chemistry proves extremely difficult even for samples from Earth. Hypotheses about the technology would require more obvious signatures, narrowband emissions, systematic trajectory changes incompatible with natural physics, or spectral characteristics that cannot be created with known cosmic chemistry. Perfect camouflage can hide such signatures, but the reference to elusive technology brings us closer to unverified speculations. The philosophical implications of any confirmed hypothesis about the existence of life within will surpass the technical discovery itself. Biology could suggest either natural panspermia or intentional seeding of star systems. The technology would imply observation, possibly assessment, potentially preparation for contact, and any discoveries would revolutionize our understanding of the distribution of life in the universe and the prevalence of intelligence throughout the galaxy. The consequences for human civilization, planetary defense strategies, and the cosmic perspective of our species will be profound and beyond current imagination. However, extraordinary claims require extraordinary evidence, and current observations are far from supporting such revolutionary conclusions. The three-eyed atlas behaves according to the natural physics of comets, even if its specific chemistry turns out to be more exotic than typical examples in the solar system. As research continues, the concept of life within serves as an important guide for evaluating evidence. It reminds us of the need to remain open to unexpected opportunities while adhering to strict standards of evidence. The universe has repeatedly surprised us throughout scientific history, but a surprise requires solid evidence, not just interesting speculations. Another radical idea begins to gain popularity in mainstream astronomical circles, offering natural explanations for cosmic seeding processes that do not require biology or technology. Part 5. Resistance from the mainstream of science. The National Aeronautics and Space Administration unequivocally classifies the Atlas three-eyed comet as an active comet, period. No official institution supports claims of extraterrestrial technology, hypotheses of artificial origin, or speculations about living spacecraft. This institutional position reflects years of accumulated wisdom regarding the difference between genuine discoveries and sensational distortions. Leading comet researchers exhibit characteristic scientific caution in response to extraordinary claims. Daryl Seligman from the University of Chicago advocates for evidence-based reasoning, emphasizing the importance of thoroughly considering natural explanations before resorting to exotic alternatives. Robert Lawler from the Planetary Science Institute shares this viewpoint, noting that unusual chemistry does not necessarily indicate artificial origins. Marco Micheli from the European Space Agency emphasizes the need for reproducible observations before making revolutionary conclusions. These experts understand that the history of astronomy contains many examples of premature excitement about seemingly impossible phenomena. Pulsars initially appeared so artificial that researchers briefly considered the hypothesis of extraterrestrial beacons. Fast radio bursts seemed incredibly energetic until the natural mechanisms became clear through theoretical research. Tabby's star exhibited strange dimming patterns, sparking speculation about extraterrestrial megastructures before explanations involving dust clouds gained acceptance. This pattern repeats constantly. Anomalous observations give rise to exotic hypotheses until patient research reveals natural mechanisms previously unknown to science. This historical precedent encourages a cautious approach in interpreting data from the three-eye atlas. The arguments of probability underlying claims of artificial origin are methodologically criticized by statistics specialists. Probability calculations made after observing specific results suffer from selective bias and sampling assumptions. When analyzing single events rather than reproducible experiments, it becomes extremely difficult to distinguish genuine anomalies from random fluctuations. Let's consider the alignment of trajectories, which some find suspicious. Critics note that any specific orbital configuration will seem unlikely if calculated retrospectively. The question is not whether this trajectory seems unlikely, but whether it represents a significant deviation from the expected behavior of interstellar objects, given our extremely limited sample size. Considering that humanity has recorded only 3 confirmed interstellar objects, making broad statistical conclusions about typical and atypical behavior is risky. What seems anomalous today may become ordinary tomorrow, as our perspective expands through studies like the Hereditary Review of Space and Time at Vera Rubin Observatory. As for non-gravitational accelerations that could indicate artificial thrust, current measurements show nothing abnormal beyond experimental uncertainties. The small forces expected from the gas emissions of a comet may remain below the detection threshold, considering the current limits of astrometric accuracy. Natural comets regularly demonstrate non-gravitational accelerations as sublimating volatile substances create effects similar to rocket thrust. These forces follow predictable patterns related to solar heating, rotation periods, and the distribution of volatile components. To detect artificial thrust, systematic deviations from these natural accelerations must be demonstrated, which remains a challenging task for the three-eyed atlas. The extraction of nickel without corresponding detection of iron has sparked significant discussions. However, experts in cometary chemistry note that such a pattern does not necessarily indicate industrial processing. Different elements have their own thresholds of excitation and intensity of radiation lines under certain physical conditions. Nickel has already been detected in comet spectra without suggesting hypotheses of artificial origin. Transition metals found in cosmic dust often display selective emission patterns depending on temperature, density, and radiation field characteristics. The absence of iron lines in specific observations cannot be considered evidence of metallurgical processing. Moreover, the analytical difficulties associated with obtaining accurate abundance ratios from the spectroscopic data of active comets should not be underestimated. Dust clouds, changing excitation conditions, and contamination from several emission regions complicate quantitative interpretation. What may seem like absent iron is more likely a reflection of observational limitations rather than its true absence. The anomalies of polarimetry that seemingly distinguish the three-eyed atlas from the comets of the solar system may have natural explanations through exotic dust physics rather than artificial engineering. In the interstellar medium, particles undergo various processing mechanisms compared to conditions in the local solar system. Bombardment by cosmic rays, interactions with stellar winds, and thermal cycling during prolonged interstellar journeys can lead to the formation of dust grains with unusual optical properties. Distributions by size, porosity levels, and changes in composition can create polarization signatures not observed in comets formed and developed in our solar system. Scientific conservatism plays an important protective role for trust in astronomical research. False positive claims about extraterrestrial technologies can undermine public trust in space science for generations to come. The community learned painful lessons from premature announcements about biosignatures in Martian meteorites, claims of bacterial life in Martian rocks that caused worldwide excitement before careful analysis revealed more down-to-earth explanations. The media's amplification effect exacerbates these fears. Speculative hypotheses presented as serious possibilities quickly transform into definitive statements during subsequent reporting cycles. Public understanding suffers when preliminary interpretations are perceived as established facts, creating unrealistic expectations of revolutionary discoveries. However, scientific resistance goes beyond simple institutional conservatism. Technical experts point out specific flaws in the arguments of exotic interpretations. The claim that orbital mechanics is unlikely actually fits within the expected ranges for randomly oriented interstellar trajectories. Chemical anomalies, while interesting, do not exceed the boundaries of the natural diversity of comets predicted for objects formed in various stellar conditions. Polar images, although unusual by the standards of the solar system, may result from dust processing mechanisms active in interstellar space but absent in our local environment. Every supposedly artificial characteristic allows for plausible natural explanations when carefully examined by specialists familiar with the relevant physics. This does not mean that unusual hypotheses lack value. Even incorrect theories can advance knowledge by prompting new observations, aiding the development of analytical methods, and forcing precise formulation of what evidence could confirm artificial origin. Speculations about extraterrestrial technology related to an object known as the Three-Eyed Atlas have sparked significant scientific activity. Detailed observational campaigns, improved spectroscopic analysis methods, and increased coordination between ground and space observation programs. These advantages accumulate regardless of whether the initial hypotheses are confirmed. The community's response also highlights healthy, self-correcting mechanisms in astronomical research. Unusual claims undergo strict scrutiny through peer review, independent verification attempts, and public debates among experts. This process, although sometimes contentious, ultimately strengthens scientific knowledge by filtering speculation from substantiated discoveries. The media spotlighted natural explanations aligned with current data while acknowledging real chemical and physical anomalies that make the three-eyed atlas scientifically intriguing. This object represents the most closely observed interstellar visitor in human history, providing unprecedented insights into the diversity of materials formed around other stars. The most convincing scientific story, emerging from accumulated observations, describes a chemically unusual but mostly natural comet. Its rich carbon dioxide composition, early volatile activity, and exotic dust properties reflect formation and evolution processes distinct from solar system examples, but not necessarily requiring artificial origin. This interpretation satisfies Occam's principle, considering all confirmed observations. It expands our understanding of the diversity of interstellar objects without resorting to unproven technological civilizations. This calls into question existing theories of comet formation and evolution while remaining based on established physical principles. As the investigation continues, the main science remains committed to evidence-based conclusions, while staying open to truly revolutionary discoveries if convincing evidence arises. The burden of proof for extraordinary claims remains quite high, protecting the integrity of astronomical research while leaving room for legitimate scientific surprises. Now we need to completely change our perspective, considering a radical hypothesis that has begun to attract serious attention from respected theorists of planet formation. There is a possibility that interstellar objects, such as the 13th Atlas, could serve as a ready source for colonizing planetary systems throughout the galaxy. This idea belongs to Suzanne Falsner. At the Max Planck Institute for Radiation Astronomy, astrophysicist Susanna Falsner proposed a revolutionary mechanism that could change our understanding of planet formation. Her hypothesis suggests that interstellar objects, wandering like the 13th Atlas, can serve as ready-made planetary cores, captured by young star systems, and quickly turning into gas giants through accretion processes. This concept elegantly solves one of the most persistent mysteries of planet formation theory. The time frames of traditional models require millions of years for dust particles to collide, stick together, and gradually form planetesimals large enough to gravitationally attract gas from protoplanetary disks. However, observations show that gas disks around young stars usually disperse in just a few million years. The mathematical problem seems insurmountable. How can planets rapidly grow massive cores to capture significant gas envelopes before the disk of their stellar hosts evaporates into space? The traditional core accretion theory faces challenges. To explain the observed number of gas giants, especially around more massive stars, Falsner's computer simulations reveal an intriguing pattern. More massive stars seem to gravitationally capture interstellar objects more effectively, and astronomical surveys indeed show a higher frequency of giant planets orbiting larger stellar masses. This correlation provides indirect support for the hypothesis of interstellar colonization. The capture mechanism works through gravitational dynamics in dense star nurseries. Young stars form in clusters containing hundreds or thousands of siblings, creating gravitationally complex conditions where interstellar objects can exchange between systems or be captured from the common galactic population. Gas friction within protoplanetary disks plays a crucial role in the capture process. When an interstellar object collides with a young stellar system, friction with the disk material can significantly reduce its speed, allowing it to gravitationally latch on. After capture, the former wandering object becomes a ready planetary core, bypassing the slow initial growth phases that hinder traditional formation models. Then the accretion process accelerates dramatically. The captured object, with a radius measured in kilometers rather than meters, has significantly increased gravitational sections to attract additional material. Growth occurs due to direct collisions with solid particles of the disk and the gravitational focusing of smaller particles, processes that can accumulate significant masses within the observed lifetimes of disks. This rapid growth of the core allows for the efficient capture of gas during the critical period when protoplanetary disks still retain their gaseous components. As a result, such planets can reach a mass comparable to Jupiter in just a few 100,000 years, rather than millions, as traditional scenarios suggest. The theoretical basis makes specific predictions about the architecture of planetary systems. Captured cores will retain chemical signatures reflecting their formation conditions in various star systems. As a result, the obtained planets may exhibit isotopic ratios, elemental compositions, or reserves of volatile substances that differ from products formed exclusively in situ. The model also predicts that the capture speed of interstellar objects should correlate with the characteristics of star clusters. Denser and more massive clusters should facilitate higher frequency capture, which may explain the observed correlations between the stellar environment and planetary system characteristics. Modern observations provide intriguing hints supporting this theory. 3 confirmed interstellar objects discovered to date. One of them is Oumuamua, the second is Borisov, and the third is Atlas, represent only the tip of a much larger population. Shifts in discoveries are heavily biased towards larger and more active objects, suggesting that smaller, inactive wanderers significantly outnumber the few we observe. This hidden population could serve as the raw material for the seeding mechanism. If interstellar space contains millions of dark inactive objects for every bright comet we discover, the supply of potential planetary cores becomes virtually unlimited on galactic timescales. The chemical diversity observed in a small sample of interstellar visitors supports the seed hypothesis. Oumuamua showed no noticeable volatile activity, indicating a composition dominated by refractory materials. Borisov resembles the comets of the solar system, indicating formation in conditions similar to our outer systems. The Atlas shows another chemical profile dominated by carbon dioxide and exotic dust properties. This diversity implies that interstellar objects encompass formation conditions in different stellar environments. Captured cores will import chemical signatures from their birth systems, which may explain the observed diversity and composition of exoplanets that modern models struggle to reproduce through purely local processes. The time of the Atlas's opening provides a unique opportunity to test aspects of the sowing hypothesis. Unlike previous interstellar objects discovered after their close approach, the early identification of this body allows for a detailed analysis of its composition and structure while it remains relatively close. If the three-eyed satin structure is typical material for sowing, its properties must reflect characteristics that promote the rapid growth of planetary cores. The composition rich in carbon dioxide indicates formation in the cold, outer regions of the system, where such volatile compounds can effectively condense. The early activity of water indicates sufficient porosity and the presence of volatile substances, which may facilitate active gas emission processes. These characteristics could be beneficial for captured nuclei. Rich in volatile substances, internal structures can facilitate rapid heating and expansion during accretion, which in turn can accelerate core growth through increased collision chances and improved particle capture efficiency. The size of the object, approximately from 0.44 to 5.6 kilometers in diameter, corresponds to theoretical predictions of effective seed masses. Smaller objects may lack sufficient gravitational influence to quickly accumulate material from the disk, while significantly larger bodies may be too rare to explain the observed frequencies of planets. Falzner's hypothesis is not just abstract theoretical assumptions. It formulates testable predictions about the properties of planetary systems, populations of interstellar objects, and correlations between characteristics of star clusters and the efficiency of planet formation. These forecasts can be assessed through current and future observational programs. The European Space Agency's Gaia mission has begun identifying potential interstellar objects through precise astrometry of star movements. The future hereditary research of Vera Rubin's observatory concerning space and time is expected to significantly expand our understanding of temporal objects, potentially revealing many additional interstellar visitors we currently do not know about. Observations with the James Webb Telescope of protoplanetary disks can detect chemical signatures corresponding to captured interstellar materials. Isotopic ratios, elemental abundances, and volatile reserves in forming planetary systems may provide indirect evidence of seeding processes. This hypothesis is also linked to broader questions about the chemical evolution of galaxies and material exchange between star systems. If interstellar seeding works effectively, the chemical history of planetary systems becomes intertwined on vast spatial and temporal scales. Star nurseries will function as mixing chambers where materials formed around various stars are redistributed among growing planetary systems. As a result, the chemical diversity obtained may exceed what could be achieved solely by local processes of formation, potentially explaining the observed ranges of exoplanet compositions. This galactic perspective transforms the formation of planets from an isolated process specific to each system into a collaborative effort involving materials and objects exchanged over interstellar distances. The consequences of this approach go beyond technical questions about formation mechanisms and touch on fundamental issues of cosmic interconnectedness and the shared legacy of planetary systems. The three eyes of the Atlas, viewed through this prism, represent not just an unusual comet or a potentially artificial probe. They become messengers carrying chemical memories from distant star systems, samples of raw materials that could form the basis for planet formation in our galaxy. Whether this particular object will ever serve such a function remains unknown. It seems destined to leave our solar system rather than join our planetary family. However, its composition and structure provide important insights into the materials available for cosmic seeding processes throughout galactic history. The hypothesis of sowing offers a natural explanation for the rapid formation of planets, which does not require exotic physics or alien technologies. She suggests that the galaxy functions as a vast recycling system, redistributing materials and allowing for the rapid growth of planets through gravitational capture and accretion. Nevertheless, even this natural seeding mechanism raises profound questions about the origin and distribution of life throughout cosmic history. To understand why the interstellar seeding process is such a revolutionary concept, we must first consider the traditional models that have defined planet formation theory for decades. The standard paradigm divides the formation of giant planets into two competing mechanics: core accretion and gravitational instability of the disk, each facing fundamental temporal issues that the seed hypothesis elegantly circumvents. The core accretion theory requires that dust particles in protoplanetary disks collide and stick together through electrostatic forces, gradually forming larger aggregates. These growing particles collide with a meter barrier, an area where aerodynamic resistance becomes so effective that objects spiral towards their stellar hosts before reaching gravitational dominance. A recent discovery of pebble accretion offered a partial solution. Instead of relying solely on random collisions, this mechanism utilizes gravitational focusing effects, allowing planetesimals to more effectively capture streams of smaller particles. However, even the accretion of pebbles takes several million years to form cores massive enough to capture gas. Gravitational instability in the disk offers an alternative route through direct gravitational collapse of dense regions in massive protoplanetary disks. This mechanism can potentially form giant planets in thousands rather than millions of years, but certain conditions in the disk are necessary: high mass, low temperature, and gravitational instability, which may be absent around most young stars. Both traditional mechanisms face strict limitations set by observations. The masses of protoplanetary disks measured around young stars often prove insufficient for the effective operation of either core accretion or disk instability. The lifespans of gas disks, limited by observations of stellar nurseries, usually range from 1 to 10 million years, which is hardly sufficient for traditional timescales of planet formation. The pressure of time becomes especially acute for massive stars, which tend to destroy their protoplanetary disks more quickly due to intense stellar winds and radiation pressure. Nevertheless, research shows that more massive stars actually tend to have giant planets more often than their less massive counterparts, which is the exact opposite of what traditional formation theory predicts. Could external seeding have occurred in our own solar system during its formation 4.5 billion years ago? This possibility remains purely speculative, but indirect evidence suggests that the speed of influx of interstellar objects may have been significantly higher in the early galaxy. Our solar system formed in a stellar nursery containing hundreds or thousands of neighboring stars born from the same giant molecular cloud. This dense medium facilitated gravitational interactions, star encounters, and potential exchanges of interstellar objects between forming planetary systems. Additionally, 3 ocular atlases may originate from the thick disk population of the galaxy. Stars formed in earlier epochs when the Milky Way had a different chemical composition and star density profiles. If this is confirmed, then this ancient heritage will testify that interstellar wanderers can carry chemical memories spanning billions of years of galactic evolution. The connection with the thick disk population opens intriguing possibilities for recycling cosmic processes operating on geological timescales. Materials ejected from planetary systems billions of years ago may eventually end up in new forming systems, creating complex networks of chemical heritage throughout galactic emptiness and time. This perspective changes our understanding of planetary system formation, transforming isolated and independent processes into interconnected phenomena, exchanging materials and evolutionary histories on vast cosmic scales. Jupiter and Saturn may contain trace amounts of materials originally formed around stars that died long before the birth of our Sun. Comparison with previous interstellar visitors illuminates how composition and activity patterns influence the interpretation of these cosmic wanderers. Two objects known as two eyes and Oumuamua represent two extreme categories of interstellar bodies. The two eyes, or Borisov, in its chemical composition, activity, and dust production, resembles typical comets of the solar system, indicating its formation in an environment similar to our outer system. Meanwhile, Oumuamua exhibits entirely different behavior. It has no detectable gas emissions, unusual acceleration patterns, and geometric constraints indicating an elongated or flattened shape, different from typical comets and asteroids. This combination of properties gives rise to speculations about artificial origins, which continue to be discussed in the context of Three Eyes, another interstellar object. Three Eyes occupies an intermediate position between these extremes. It shows clear cometary activity through gas and dust ejections, but its chemical signatures are noticeably different from both solar comets and Two Eyes. This intermediate position makes it particularly valuable for understanding the full spectrum of interstellar objects. The chemical diversity among our small number of interstellar visitors hints at various formation conditions, reflecting different architectures of star systems, evolutionary histories, and epochs of galactic chemical evolution. Each object carries unique imprints of its birthplace, potentially allowing for retrospective studies of conditions around other stars. Estimates of the frequency of interstellar objects remain quite uncertain, but recent theoretical work suggests that our solar system may encounter several objects a year in the size range of Three Eyes. Most of them remain unnoticed due to their small size, inactive nature, or unfavorable observation geometry. The Vera Rubin Observatory, set to begin operations in the mid-20s, is expected to revolutionize our tracking of transient objects, including interstellar visitors. This observatory will monitor the entire visible sky every few nights, detecting moving objects by comparing sequential images. Statistical projections suggest that Rubin will be able to identify hundreds of interstellar objects annually after reaching full operational capacity. This sharp increase in sample volume will allow for reliable testing of hypotheses about population characteristics, size distribution, and patterns of chemical diversity. Improved detection capabilities will also enable more accurate assessments of capture probabilities in young star systems. If interstellar objects turn out to be much more numerous than currently assumed, it significantly increases the resources available for colonization mechanisms. The principles of colonization make specific predictions about the correlations between the properties of star clusters and the architecture of forming planetary systems. Dense and massive clusters should contribute to higher rates of capture, which may explain the observed relationships between the stellar environment and the frequency of planet formation. These predictions become verifiable through the combination of Gaia astrometry data tracking star formation associations with exoplanet studies, characterizing the properties of planetary systems around stars with known formation conditions. Statistical analyses can reveal signs of seeding processes occurring in the early stages of planetary system formation. The historical context also includes broader questions about the chemical evolution of galaxies and material redistribution processes. If the seeding process has been effectively working throughout cosmic history, the chemical signatures of planetary systems are intertwined on vast spatial and temporal scales. This perspective of galactic mixing suggests that the chemical diversity observed in the atmospheres and compositions of exoplanets may exceed what can be achieved solely by local formation processes. The range of available materials significantly expands when formation regions can import components initially condensed around stars with various masses, metallicities, and evolutionary histories. The object called Three Eyes Atlas, in this historical perspective, represents a unique opportunity to study materials that might have participated in seeding processes, even though this particular object seems intended for interstellar escape rather than for capturing our solar system. The combination of early discovery, detailed observational campaigns, and modern analytical methods provides unprecedented insights into the composition and structure of potential sewing materials. Regardless of whether the three-eyed atlas ever functioned as a planetary core, it provides important data for understanding the types of objects available for cosmic seeding throughout galactic history. The hypothesis of sewing transforms interstellar objects from mere curiosities into potential architects of planetary diversity, suggesting that worlds in our galaxy may have more complex hereditary connections than previously thought. Part 8. The Three-Eyed Atlas as a Test Case. The dominance of carbon dioxide observed in Three Eyes Atlas provides our first important test of the seeding hypothesis. This chemical signature may indicate formation in conditions much colder and richer in carbon dioxide than typical comet formation areas in the solar system. Such extreme conditions could exist at the outer boundaries of massive protoplanetary disks or around low-mass stars with extended snowline boundaries. For seeding purposes, such a composition profile could prove advantageous rather than anomalous. Carbon dioxide remains stable at higher temperatures than water ice, potentially allowing volatile substances to evaporate more actively at greater distances from stars. A seed with a high carbon dioxide content could remain active during capture phases when water-dominating objects remained inactive. Early hydroxyl activity detected at 3.5 astronomical units demonstrates that 3I's Atlas contains a significant amount of water ice despite its carbon dioxide-rich coma. This combination suggests the presence of a layered or mixed volatile structure, capable of producing both early water signals and sustained carbon dioxide emissions as solar heat penetrates deeper into the core. Such complex architecture of volatile substances can be useful for captured particles, providing several mechanisms for enhancing and improving particle capture during accretion. Early water outbursts can create extended atmospheres, increasing the likelihood of collisions with disk materials. Later, carbon dioxide emissions may sustain this process over longer timescales and at greater orbital distances. Polar imagery measurements demonstrating unusual properties of dust reinforce the hypothesis of exotic formation conditions. Extended negative polarization and characteristic scattering behavior indicate populations of grains with porosity levels, size distributions, or composite characteristics differing from those of solar system comets. These properties of dust can reflect processing and interstellar conditions over long periods. Bombardment by cosmic rays, interactions with stellar winds, and thermal cycles over millions of years of travel between stars can modify grain structures in ways impossible within individual star systems. The unusual properties of dust can enhance the efficiency of accretion through several mechanisms. Materials with high porosity have larger geometric cross-sections compared to their masses, improving the likelihood of collisions with disk particles. Characteristic optical properties can indicate chemical compositions, especially effective for catalyzing subsequent grain growth processes. Size constraints derived from observations using the Hubble telescope place the diameter of the 3I Atlas object in the range of approximately 0.4 to 5.6 kilometers, which occupies a potentially optimal zone for seeding efficiency. Large enough to exert significant gravitational influence, but small enough to be effectively captured by gas friction in protoplanetary disks. Objects significantly smaller than this range may not have enough mass for rapid accretion of disk materials. Significantly larger bodies may be too massive for effective capture, requiring excessively specific collision geometries to achieve gravitational binding in young star systems. The intermediate size also implies that the Tri-Eye Atlas serves as accessible raw material for seeding processes rather than rare, massive planetesimals. Theoretical models suggest that objects in this range can form relatively abundantly through collisional grinding of larger bodies or direct condensation in disk regions. Cinematic analysis suggests the possible origin of the Tri-Eye Atlas from thick disks, indicating its formation in earlier epochs of galactic evolution, when star densities, metallicities, and chemical processing mechanisms significantly differed from modern conditions. This ancient legacy may provide information about the materials for sewing available in the early phases of the universe. If confirmed, the connection to the thick disk structure suggests that the Tri-Atlas holds chemical memories spanning potentially billions of years. Isotopic ratios, elements, and the molecular composition preserved in its core can reflect the conditions that existed during the epochs of star formation preceding the birth of our solar system. This temporal perspective transforms the Tri-Atlas from a modern object of interest into an archaeological specimen of ancient galactic chemistry, potentially containing elements that originally formed around stars that completed their life cycles before our sun began nuclear fusion. The discovery of cyanides strengthens the chemical composition available for seeding processes, confirming the presence of complex carbon-nitrogen chemistry in the core. The emission of CN is usually associated with the sublimation of organic compounds, suggesting that the Tri-Atlas contains molecular building blocks that predate life, along with its unusual volatile mixture. For seeding scenarios involving chemical precursors of life, this organic content may prove crucial. Objects containing diverse organic reserves can deliver complex chemistry directly to forming planetary systems, potentially accelerating prebiotic evolution processes in newly formed worlds. The lines of nickel radiation, while not necessarily indicating industrial processing, demonstrate that the Tri-Atlas contains refractor elements alongside volatile components. This mixed composition provides both the volatile substances necessary for active gas expulsion and the solid materials required for significant planetary core construction. The combination of volatile and refractor components in one object offers advantages for sewing mechanisms. Volatile substances ensure rapid expansion and improved particle capture in the early phases of accretion. Refractory materials provide a solid foundation necessary for stable gravitational growth towards planetary masses. Spectroscopic analysis reveals additional chemical complexity through the detection of numerous emission lines spanning various molecular and atomic species. This chemical diversity suggests formation in conditions capable of preserving a wide range of materials, rather than in highly processed environments that may characterize exclusively local formation scenarios. Preserving chemical diversity in the Tri-Atlas implies minimal thermal processing during its interstellar journey. This conclusion supports the possibility of transporting complex chemistry across interstellar distances without completely destroying molecules due to cosmic ray bombardment or heating from encounters with stars. Current observations show that the 3I Atlas object possesses several characteristics of effective seed material. It has the appropriate size, a complex chemical composition, a mixed volatile and fire-resistant nature, as well as exotic signs of formation. However, direct testing of the seeding effectiveness is impossible, as this object seems designed for interstellar escape. The capture dynamics required for seeding demand specific collision geometries with young star systems that have massive protoplanetary disks. Currently, the Tri-I Atlas is moving along a hyperbolic trajectory that will take it out of our solar system after completing its current passage. This escape trajectory provides valuable scientific opportunities, allowing for a detailed study of the composition and structure of the seed material without the complications of constant gravitational capture. We can analyze the Tri-I Atlas as a representative sample while it is accessible to our observational capabilities. The chemical characterization conducted through observations with several telescopes will establish benchmarks for recognizing similar materials in other contexts. Future discoveries of captured interstellar objects in exoplanetary systems can be identified by comparing them to the detailed composition currently being assembled for the Tri-I Atlas. Isotopic ratios, elemental abundances, and molecular reserves measured during the current observational campaign will become benchmark standards for distinguishing between seed materials and those formed locally in planetary systems. This approach to creating a reference data library may allow for the retrospective identification of seeding signs in mature planetary systems. Thus, the Tri-I Atlas serves a dual scientific role. It checks the plausibility of the characteristics of the sewing material and establishes observational benchmarks for recognizing sewing processes in other star systems. Regardless of whether this particular object participated in the formation of planets, it provides important information about the raw materials available for cosmic seeding throughout galactic history. The final verdict on the Tri-I Atlas as a seed material remains preliminary but encouraging. It demonstrates numerous characteristics corresponding to the effective composition and structure of seeds, providing unprecedented opportunities for detailed analysis of the properties of an interstellar object. However, if seeds are regularly moved between star systems, carrying complex chemistry and diverse materials, can they also transport the most complex chemistry of all, the molecular foundations of life? The concept of an interstellar object as a cosmic courier fundamentally changes our understanding of material exchange between star systems. Instead of isolated islands of chemistry, planetary systems become nodes in an expansive galactic network where organic matter and minerals move through gravitational flows spanning light years and eons. This cosmic cross-pollination occurs on timescales that far exceed human experience, yet are short-term on a galactic scale. One interstellar object can transport materials between dozens of encounters with stars over millions of years, traveling through the gravitational landscape of the galaxy. Each encounter provides the opportunity for capturing, delivering, or exchanging chemical cargo accumulated from previous visits to star systems. The statistical consequences seem astonishing when viewed on the scale of the galactic population. Our galaxy, the Milky Way, contains about 400 billion stars, most of which likely had protoplanetary disks in their youth. Even a small part of these systems exchanging materials through the transportation of interstellar objects would create a chemical mixture on an unprecedented scale. This perspective is directly related to the hypotheses of panspermia, the possibility that the ingredients for life or life itself can travel between worlds on natural spacecraft. The traditional version suggests that stones ejected from planetary surfaces carry dormant microbes to new homes among the stars. However, interstellar objects offer a more elegant mechanism, specially designed ships optimized for interstellar survival and chemical preservation. Unlike ejecta, which usually come from planetary surface materials, interstellar objects likely form samples of deeper, primitive compositions that have undergone minimal thermal processing. These primordial chemical reserves can preserve complex organic molecules, isotopic signatures, and even biological materials over interstellar distances. The question of survival remains central to assessing panspermia scenarios. Bombardment by cosmic rays poses a major threat to complex chemistry during long interstellar journeys. However, calculations show that several meters of ice and dust, easily accessible in objects like the three eyes of Atlas, can reduce radiation exposure to biologically acceptable levels. Recent theoretical studies have refined these survival estimates, taking into account the protective effects of magnetic fields generated within objects, conductive materials, mechanisms of chemical reduction that can operate even at low temperatures, and statistical distributions of cosmic ray impacts creating radiation shadows inside objects. The results suggest cautious optimism regarding the preservation of complex organic chemistry, although the survival of actually living organisms remains a matter of speculation. A more conservative scenario suggests delivering prebiotic building blocks rather than fully functional biological systems, which is still revolutionary for understanding the cosmic spread of life. Statistical forecasts based on improved data about interstellar objects suggest that collisions with our solar system occur much more frequently than might be apparent from 3 confirmed detections. Most visitors probably go unnoticed due to their small size, inactive nature, or unfavorable conditions for observation from the ground. The anticipated census at the Vera Rubin Observatory is expected to significantly expand our statistical sample, potentially revealing hundreds of interstellar visitors each year. This enhanced detection level will allow for reliable hypothesis testing on SOING, as well as provide numerous opportunities to study various chemical compositions and structural characteristics. If Rubin's forecasts are accurate, the supply of raw materials for seeding mechanisms will become virtually limitless on a cosmic timescale. Young star systems will regularly encounter potential seeding materials, making capture events statistically inevitable rather than exceptional. The chemical diversity, already noticeable among our small sample of interstellar objects like Oumuamua, Borisov, and Atlas, hints at the variety of materials obtained from different star formation environments, evolutionary histories, and epochs of galactic chemical evolution. This diversity suggests that seeding processes can import chemical signatures covering the entire spectrum of galactic metallicity evolution, star mass distributions, and types of planetary system architectures. The resulting chemical mixture can lead to the formation of planetary compositions that surpass what can be achieved by local processes alone. The lack of active flight from Oumuamua, along with its unusual geometric constraints, suggests formation in environments predominantly composed of refractory materials. Borisov, which closely resembles objects in the solar system, likely formed under conditions similar to our outer planetary regions. Atlas has a completely different chemical profile, dominated by carbon dioxide and exotic dust properties. This spectrum of compositions implies that various star systems contribute their unique chemical signatures to the population of interstellar objects. Massive stars can eject carbon-rich materials from their vast protoplanetary disks. Low-mass stars can contribute water-rich compositions that form in their cooler, expanded regions beyond the snowline. The temporal aspect adds additional complexity to this chemical mixing process. Objects like Atlas, potentially originating from thick disk populations, may carry chemical memories of galactic epochs billions of years ago. Their compositions might reflect stellar formation conditions that no longer exist in the modern galaxy. This archaeological perspective turns interstellar objects into time capsules preserving ancient galactic chemistry. Isotopic ratios, elemental abundances, and molecular inventories can reveal unique insights into the cosmic chemical evolution that are inaccessible through traditional astronomical observations. Although the idea of transferring life sounds speculative, It deserves serious attention considering the possible consequences. If interstellar objects regularly transfer the chemistry of previous life between star systems, then the emergence of life may be much more likely than calculations based solely on local chemical evolution suggest. Such a distributed approach to prebiotic chemistry could function like an extensive mycelial network covering galactic distances. Each star system becomes a node where complex molecules accumulate, evolve, and spread to neighboring systems through the transport of interstellar objects. The cumulative chemical evolution can significantly exceed what a single system can achieve on its own. Nevertheless, survival issues remain serious, considering the geological ports and timescales characteristic of interstellar travel. Radiation, thermal fluctuations, and chemical decomposition processes can destroy complex organic molecules long before they reach suitable delivery targets. A more realistic scenario suggests delivering simpler organic building blocks rather than complex biomolecules or living organisms. Even this conservative version will be revolutionary, showing that the chemical foundations of life can be distributed throughout the galaxy rather than arising independently in every suitable environment. Recent advancements in extremophile biology have shown that organisms can survive in conditions previously thought impossible for life. Some bacteria withstand radiation doses thousands of times higher than previous estimates of biological limits. Others remain viable for decades in complete vacuum or at temperatures close to absolute zero. These discoveries expand the parameter space for possible biological survival during interstellar transport, although the combination of several extreme conditions over millions of years of travel still poses outstanding challenges, even for the most resilient known organisms. The ethical and philosophical implications of confirmed cosmic transfer, whether of natural or artificial origin, extend far beyond technical questions about the mechanisms of planet formation. If worlds across the galaxy share a common chemical heritage through processes of material exchange, the boundaries between local and alien chemistry become meaningless. This galactic perspective suggests that Earth's biosphere may include materials originally formed around countless other stars over billions of years of cosmic evolution. Our planet is becoming not an isolated world, but a shared creation involving the chemical contributions of the entire galactic community. The three-eyed atlas, viewed through this prism, represents much more than an unusual comet or a potential artificial probe. He transforms into a messenger carrying chemical substances, memories of distant star environments, a sample of materials that may have participated in seeding processes throughout cosmic history. It remains unknown whether this particular object delivered its cargo to a receptive young planetary system, but its composition and structure provide unprecedented information about the materials available for cosmic cross-pollination throughout the evolutionary history of our galaxy. Can some seeds carry not only chemistry? Can they transport real biology, being designed to create the conditions necessary for planet formation? Part 10. The concept of a living planetary seed. The synthesis of two radical ideas, interstellar objects as planetary seeds and the possibility of life within these cosmic wanderers, creates perhaps the most speculative yet fascinating scenario in our exploration. What if the three eyes of the Atlas are not just a system for delivering chemicals, but a living spacecraft designed to fundamentally change the process of planet formation? Scenario A. Imagine sleeping microorganisms enclosed in a sturdy matrix rich in carbon dioxide, providing both protection and nourishment during millions of years of interstellar travel. These microscopic passengers would remain in a cryptobiotic state, their metabolic processes slowing to imperceptible rates, while cosmic radiation slowly destroys their cellular mechanisms. The prevalence of carbon dioxide observed in the three eyes of the Atlas can perform many biological functions. This molecule provides excellent protection against radiation while remaining chemically stable at extreme temperatures. In addition, carbon dioxide can serve as a source of carbon for autotrophic organisms capable of fixing atmospheric carbon into organic compounds when conditions allow. During warm passages near stellar encounters, internal heating can create temporary zones of liquid water within a porous matrix. These fleeting oases could awaken dormant biology, allowing for rapid reproduction, metabolic activity, and the spread of biological materials into the environment through reproduction processes. Speculative biology would have to demonstrate exceptional resilience characteristics, significantly surpassing any known earthly organisms. Resistance to doses of cosmic radiation accumulated over geological timescales, survival in vacuum conditions, tolerance to extreme temperature fluctuations, and the ability to remain viable without metabolic activity for millions of years. Recent discoveries of extremophils on Earth provide intriguing hints that such possibilities may exist in the realm of biological capability. Deinococcus radiodurans survives radiation levels thousands of times beyond lethal doses for most life forms. Tardigrades withstand vacuum conditions, extreme temperatures, and decades of complete desiccation, remaining viable after rehydration. Scenario B delves into even more speculative ideas, including the creation of probes that consciously affect the material of the protoplanetary disk through controlled ejections aimed at optimizing planet formation conditions. Instead of being passive seeds waiting to be captured, these objects can actively participate in the terraforming of entire star systems. The cloud of dust observed in the Atlas trio could theoretically represent a deliberate introduction of material into the space environment of our solar system. If the object contains programmable substances or self-regulating systems, the emission patterns may follow complex algorithms designed to achieve specific chemical or physical goals. This scenario requires technology capable of functioning autonomously for millions of years, adapting to unpredictable conditions when interacting with various star systems. Engineering challenges seem almost insurmountable with any conceivable technology, yet the concept remains theoretically possible for sufficiently advanced civilizations. Observed signatures that could distinguish such exotic scenarios from natural phenomena include recurring jet patterns correlating with programmable targets rather than solar heating cycles. Course corrections incompatible with the natural physics of sublimation may indicate active orientation control systems. Narrowband emissions at certain frequencies may suggest the presence of communication systems or technological power sources. Current observations show none of these decisive technological signatures. The Atlas trio behaves according to the natural physics of comets across all measurable parameters, demonstrating emission patterns that predictably correlate with solar heating and rotation dynamics. The absence of obvious artificial signatures does not completely rule out exotic hypotheses, but requires increasingly complex explanations of why advanced technology remains fully concealed, achieving complex goals through seemingly natural processes. The question of why now adds another layer of complexity to artificial scenarios. If Atlas represents targeted reconnaissance or terraforming technologies, why does it manifest in this era of human technological development? Abraham Loeb's interpretation suggests that perihelion passage behind the Sun may reduce observational capabilities from ground-based telescopes, ensuring operational security for sensitive actions. However, this explanation assumes that hypothetical extraterrestrial civilizations have detailed knowledge of human observational capabilities, unaware of our extensive astronomical infrastructure in orbit. The philosophical aspects of confirmed scenarios with living seed planets would fundamentally change human understanding of our cosmic context and responsibilities. If we imagine that the galaxy functions as a vast gardening system, where intelligent seeds form planets, then our humanity may be the result of deliberate cultivation rather than random evolutionary processes. This viewpoint raises profound questions about autonomy, purpose, and responsibility. Does humanity have an obligation to continue such hypothetical gardening actions? Should we attempt to contact the gardeners? How will confirmed cultivation affect humanity's cultural and religious beliefs based on assumptions of cosmic isolation? These ethical questions become even more complex if the processes of sowing occur through biological rather than technological mechanisms. Natural panspermia suggests that life throughout the galaxy shares a common ancestor, making all biological systems distant relatives separated by space and time, rather than primary evolutionary barriers. Scenarios of artificial seeding raise questions about the intentions and possibilities of hypothetical cosmic gardeners. Benevolent cultivation aimed at maximizing the spread of life throughout the galaxy implies entirely different relationships with potential alien civilizations compared to scenarios involving observation, manipulation, or exploitation. Currently, observational data does not confirm unusual biological or technological interpretations of the object called the three-eyed atlas. This object demonstrates chemical and physical anomalies that intrigue scientists while remaining fully consistent with the processes of natural formation and evolution. Nevertheless, speculative scenarios serve important functions by expanding conceptual horizons and encouraging the development of more sophisticated methods for detecting genuine biological or technological signals, if they exist in other contexts. The burden of unusual evidence remains at the proper height for claims concerning biology or technology of interstellar objects. The scientific method requires reproducible evidence rather than speculative interpretations of ambiguous observations, yet the philosophical value of exploring these concepts transcends their immediate scientific plausibility. They compel a reconsideration of the assumptions about life's distribution in the cosmos, the role of intelligence in shaping planets, and humanity's place in potentially vast networks of biological or technological activity. The concept of a seed planet also emphasizes the interconnectedness of cosmic processes, which can operate on scales from individual molecules to entire galactic populations. If life participates in the formation of planets both naturally and artificially, the boundaries between geology, biology, and technology become increasingly insignificant. The three-eyed atlas, regardless of whether it ultimately proves to be natural, biological, or technological, has already expanded human perception of the possibilities hidden in cosmic phenomena that initially seem mundane. The investigation process demonstrates science's ability to seriously consider radical hypotheses while maintaining strict standards of evidence evaluation. The speculative nature of scenarios about the life seeds of planets does not diminish their value for stimulating the improvement of observation methods, developing theoretical foundations, and philosophically contemplating humanity's cosmic context. Even incorrect hypotheses can advance knowledge by clarifying what evidence will constitute proof of unusual claims. As the three-eyed atlas continues its journey to perihelion, the accumulating observational data will ultimately determine which interpretation, natural, biological, or technological, best explains this mysterious visitor from the space between the stars. The next 6 to 12 months may provide the final data necessary to resolve these fundamental questions about the nature of our interstellar visitor and its significance for understanding planet formation, the distribution of life, and the role of intelligence in cosmic evolution. Part 11. Upcoming observations. October the 3rd, 2025 will mark the first significant date of observations, marked by the approach of the three-eyed atlas to within approximately 30 million kilometers of Mars. The European Space Agency confirmed that Mars Express and the ExoMars Trace Gas Orbiter will attempt coordinated observations using their high-resolution stereo cameras, color, and stereoscopic imaging systems of the surface, as well as additional specialized instruments. The Mars Reconnaissance Orbiter was also mentioned in several sources as a potential participant in this observation campaign. Although scheduled conflicts with current ground operations may limit its availability, each tool offers unique opportunities to analyze the structure of comas, jet patterns, and color variations that can help distinguish natural emissions from artificial ones. The proximity to Mars offers unprecedented opportunities for high-quality imaging at wavelengths unavailable to ground-based telescopes, eliminating atmospheric distortions and allowing temporary tracking of emission changes over several rotational periods. The spectroscopic capabilities of orbital spacecraft around Mars can detect emission lines invisible from Earth due to atmospheric absorption or insufficient spectral resolution. The discovery of additional molecular species, unusual isotopic ratios, or signs of artificial emissions will significantly alter interpretations of the nature and origin of the three-eyed atlas. October 29th will be the moment of perihelion at a distance of approximately 1.3600 astronomical units from the Sun. Unfortunately, from Earth's perspective, this cosmic alignment, being behind our Sun, prevents direct observation by most ground-based and orbital telescopes at the critical moment when solar heating reaches maximum intensity. However, several celestial objects located at Lagrange point 0.1, or within the inner part of the solar system, can maintain a line of sight with the three-eyed atlas during perihelion. The Solar and Heliospheric Observatory, Parker Solar Probe, and the upcoming Polar Emitter, which will combine the emission of the corona and heliosphere, may observe the object at the moment of its closest approach to the Sun. These observations will capture the three-eyed atlas during its peak activity, when the sublimation rate reaches its peak, and any artificial systems can most clearly manifest their technological signatures. Intense solar radiation during perihelion can trigger reactions in hypothetical biological or technological components that remain inactive at great distances. Observations from Mars may provide limited angles of view on the perihelion area, although the geometry remains complex for detailed analysis. The combination of various perspectives from different spacecraft can enable a three-dimensional reconstruction of the coma structure and eruption patterns, which cannot be achieved with single observation platforms. In early December 2025, the return of terrestrial observation capabilities is expected when the three-eyed Atlas emerges from behind the solar disk, allowing for renewed telescopic access. The James Webb Space Telescope is ready to resume detailed spectroscopic analysis with significantly improved sensitivity compared to observations before perihelion. Ground observatories around the world will coordinate intensive monitoring campaigns to document any changes in chemical composition, eruption patterns, or physical structure resulting from intense solar heating during perihelion passage. The Vera Rubin Observatory can conduct high-frequency observations, tracking changes in brightness and morphological evolution. The post-perihelion phase presents important challenges for distinguishing natural evolution from artificial behavior. Natural comets typically show predictable changes in the rates of volatile production, dust emission patterns, and coma chemistry after close encounters with the Sun. Any deviations from the established physics of sublimation may indicate artificial control systems or biological reactions to changes in the environment. December 19, 2025 presents an optimal window for observation from Earth when the three-eyed Atlas will be approximately 1.18 astronomical units away. Close enough for detailed study, yet far enough to avoid solar interference. This geometry allows for comprehensive analysis using the most powerful astronomical tools of humanity without complications related to proximity to the Sun. The Hubble Space Telescope and the James Webb Space Telescope will coordinate unprecedented spectroscopic studies covering ranges from ultraviolet to infrared. These observations can reveal isotopic signatures, uncovering formation conditions, organic compounds indicating prebiotic chemistry, or artificial emission lines indicating technological origins. Ground-based observatories, including the Very Large Telescope, Keck Observatory, and the Quieter Large Millimeter Array, will provide additional data ranging from radio waves to optical wavelengths. The coordinated campaign is the largest study ever conducted to examine an interstellar object under optimal observation conditions. On March 16, 2026, the mission will conclude when the three-eyed Atlas approaches within 0.36 astronomical units of Jupiter. This close encounter provides the opportunity to utilize the resources of the Jupiter system, although real conditions limit the available observational capabilities. Proposals have been published suggesting that NASA's Juno spacecraft could alter its trajectory to observe the three-eyed Atlas during its encounter with Jupiter. However, these proposals remain theoretical exercises rather than approved mission extensions. Fuel restrictions, operational risks, and the priorities of fundamental science make such trajectory changes extremely unlikely without compelling evidence of unusual phenomena. The spacecraft Psyche, currently heading towards its target, an asteroid, may provide remote sensing capabilities if the geometric conditions are favorable. Similarly, the mission of the European Space Agency, Jupiter's Moons Explorer, may potentially observe the three-eyed Atlas from a distance, although such observations will be secondary tasks rather than the main activities of the mission. The geometry of meeting Jupiter offers unique opportunities for experiments in gravitational physics. Precise tracking of the trajectory of the three-eyed Atlas during a close approach can reveal slight deviations from purely gravitational predictions, which may indicate artificial propulsion systems or unusual mass distributions within this core. The intense radiation environment around Jupiter may provoke reactions from hypothetical biological or technological components that remain inactive in normal interstellar conditions. Any artificial systems designed to operate in high radiation conditions can best demonstrate their capabilities at this stage of the mission. NASA's resource list for the three-eyed Atlas observation campaign resembles an inventory of humanity's greatest space tools. The Hubble Telescope, James Webb Telescope, Exoplanet Survey Satellite, Neil Gehrels Swift Observatory, Sphere X, rovers and orbiters, Parker Solar Probe, Punch, Solar and Heliospheric Observatory, Europa Clipper, Jupiter's Moons Explorer, Lucy, and Psyche represent unprecedented coordinated efforts spanning multiple space agencies and scientific disciplines. This large-scale coordination project reflects the recognition of the scientific community that the three-eyed Atlas represents a unique opportunity to deepen our understanding of interstellar objects planet formation processes, and potentially revolutionary discoveries about life or intelligence in space. The temporal sequence of observations allows for numerous independent tests of hypotheses about the nature and origin of the three-eyed atlas, while early observations of Mars establish basic patterns of activity. Reaction tests to extreme heating during perihelion passage, as well as observations of Earth post-perihelion, document evolutionary changes. Encountering Jupiter provides definitive tests of the gravitational and radiation environment. Each phase of observations has its specific capabilities and limitations that complement other elements of the campaign. Martian orbiters offer high spatial resolution, but have limited spectroscopic capabilities. Earth-based telescopes provide full spectral coverage but suffer from atmospheric interference. Spacecraft eliminate atmospheric effects but have wavelength limitations due to specific instruments. Coordination challenges represent significant achievements in international scientific collaboration, requiring the alignment of observations among multiple space agencies, prioritizing limited observation time on congested objects, and coordinating data analysis efforts that demand an unprecedented level of cooperation. The timeline of the observational campaign spans 8 months of intensive monitoring using humanity's most advanced astronomical instruments. Never before have we had such comprehensive capabilities to study an interstellar visitor during its passage through the solar system. The volumes of data expected from this campaign will require new approaches to storage, analysis, and interpretation. Algorithms for machine learning, automated spectral analysis techniques, and data sharing protocols are being developed specifically to process the unprecedented flow of information from the observations of the three-eyed atlas. However, the ultimate value of this observational abundance entirely depends on what the data reveals about the fundamental nature of our mysterious visitor. The most advanced tools in human history are ready to detect signals that could revolutionize our understanding of planet formation, the distribution of life in space, or the role of intelligence in galactic evolution. The next stage of our research must determine what these remarkable tools can reveal and what evidence will clearly separate natural phenomena from unusual alternatives that continue to captivate scientific and public imagination. Part 12. What data can reveal? Isotopic spectroscopy may be our most powerful tool for determining where the three-eyed atlas originally formed in the vast chemical landscape of the galaxy. The ratios of heavy hydrogen to hydrogen in water vapor, carbon-13 to carbon-12 in carbon dioxide, nitrogen-15 to nitrogen-14 in hydrogen cyanide, and oxygen-18 to oxygen-16 in various compounds serve as chemical fingerprints, preserving the conditions of formation and environment on geological timescales. Each star system has unique isotopic signals reflecting specific nuclear processes, the history of chemical evolution, and environmental conditions present during planet formation. Extreme isotopic ratios compared to the norms of the solar system may indicate formation around stars of varying mass, metallic content, or evolutionary stages, providing important data about the birthplace and history of three ocular atlases. The ratio of heavy hydrogen to hydrogen is particularly informative, as its content varies significantly under different cosmic conditions. Formation in the cold outer regions of the disk leads to higher enrichment with heavy hydrogen compared to the warm conditions of the inner system. Interstellar processing can also alter these ratios through selective photodissociation and chemical fractionation. Tracking the evolution of gas chemistry provides a powerful tool for distinguishing natural sublimation physics from artificial control systems. Natural comets demonstrate predictable changes in the ratio of carbon dioxide to water, the rate of carbon monoxide production, and volatile substances. The models of emergence change as solar heat penetrates deeper into the layers of the core. Artificial systems can display evolutionary patterns of chemistry that systematically deviate from temperature-driven sublimation models. Controlled emissions of volatile substances, synchronized sequences of emissions, or chemical compositions that remain unchanged despite fluctuations in solar heat could indicate active management rather than passive thermal processing. The unmatched spectroscopic sensitivity of the James Webb Telescope allows for the detection of trace molecules invisible to previous generations of instruments. Complex organic compounds, unusual isotopic variants, or artificial emission signatures may emerge due to the enhanced data quality achieved through infrared spectroscopy in space. Measurements of non-gravitational acceleration provide the most direct test for artificial propulsion systems operating below current detection thresholds. High-precision astrometry, combined with occultation timing observations, can potentially detect signals akin to a push, up to about 10 to the minus 13th astronomical units per day squared. This level of sensitivity approaches the theoretical limits set by solar radiation pressure and natural boiling forces, allowing for final tests on artificial acceleration signatures that exceed the behavior of natural comets. Constant directional accelerations, incompatible with forces caused by sublimation, could serve as compelling evidence of the existence of propulsion technology systems. The absence of abnormal accelerations in modern datasets indicates either a natural origin of the three-eyed atlas or the extremely subtle nature of possible artificial propulsion systems. More precise measurements during upcoming observations could significantly refine these constraints. The analysis of the comet's morphology, using high-frequency imaging from Martian orbiters, may reveal periodic patterns of jets, geometric symmetries, or structures that are independent of sunlight and indicate active control systems rather than a passive thermal response. Natural comets typically exhibit jet activity that correlates with rotation periods and solar heating, following predictable thermodynamics. Artificial jets can operate on temporal sequences unrelated to natural thermal cycles, maintain directions inconsistent with temperature gradients, or exhibit brightness changes following programmable rather than physical patterns. High spatial and temporal resolution available from observations from Mars allows for detailed analysis of jet behavior, which is impossible with ground-based telescopes. Mission planners from the European Space Agency confirmed that Mars Express and ExoMars Trace Gas Orbiter have sufficient capabilities to detect jet structures at a kilometer level during the approach on October 3rd. This permission allows for a morphological analysis comparable to detailed studies of comets in the solar system. Measurements of polarimetric dust continue to map negative polarization and phase angle behavior that distinguish the three-eyed atlas from typical comets of the solar system. These optical properties reflect the main characteristics of particles, including size distribution, porosity levels, composition variations, and internal structures that preserve the signatures of formation conditions. Natural explanations for the unusual polar visualization may include exotic particle reprocessing during long interstellar journeys, the formation of dust condensation under different physical conditions, or compositional differences reflecting non-solar stellar chemistry. Artificial explanations may relate to specially designed particles intended for specific optical or physical properties. The distinction between exotic natural processes and artificial engineering remains a complex challenge when using only polar visualization. However, combined with other diagnostic methods, the unusual optical behavior contributes to the overall recognition system necessary for final classification. The detection of metals and organic compounds represents another important diagnostic boundary, where improved instrumental capabilities can reveal crucial evidence for determining natural or artificial origins. The current detection of nickel without corresponding iron signatures piques researchers' interest, remaining consistent with the effects of natural excitation and abundance. Future observations will focus on the search for additional metallic elements, complex organic molecules, and isotopic variations that may indicate both exotic natural chemistry and artificial processing. The discovery of clearly artificial molecular signatures that cannot be produced by known cosmic chemistry will be compelling evidence of technological origin. The discovery of complex organic chemistry using the enhanced sensitivity of the James Webb Telescope may reveal prebiotic compounds compatible with panspermia scenarios or artificial biochemical signatures indicating the presence of biological cargo. The distinction between natural and artificial organic compounds requires detailed molecular analysis that exceeds current observational capabilities. The tree of observational outcomes branches into three main possibilities based on accumulated patterns of evidence. The Exit A describes a natural comet with unusual chemistry that expands our understanding of the diversity of interstellar objects while remaining fundamentally consistent with known physics and formation processes. This scenario will establish the artifact as a crucial calibration point for models of interstellar object populations, showcasing the chemical diversity available through processes of cosmic material exchange. The scientific value of this discovery will be significant, even without revolutionary consequences for life or intellect. The Exodus B encompasses a natural composition resembling seeds, supporting Susanna Falsner's hypothesis about the seeding of planets, while remaining entirely within the framework of natural processes of formation and evolution. This scenario will provide important evidence of the mechanisms of cosmic material exchange that accelerate planet formation without requiring biological or technological explanations. The consequences for the theory of planet formation will be revolutionary, demonstrating that interstellar objects actively participate in the architecture of planetary systems, rather than being merely curious byproducts of dynamic evolution. Exit V represents an exceptional opportunity of confirmed technological signatures indicating artificial origin, biological cargo, or engineering capabilities significantly surpassing human achievements in technology. This scenario carries enormous consequences, but the likelihood of its realization remains extremely low based on current patterns of evidence. The burden of proof for the outcome V remains correspondingly high, requiring several independent lines of evidence that definitively rule out natural explanations. Single anomalous measurements or ambiguous signatures will be insufficient for such revolutionary conclusions. The scientific method requires reproducible evidence, not speculative interpretations of random observations. Any confirmed technological signatures will require verification through independent observational campaigns using various tools and analytical methods. The importance of accurate classification cannot be overstated. False positive results indicating artificial origin can undermine scientific reputation for decades and lead to improper political decisions. False negative conclusions may miss real opportunities to deepen human knowledge about the distribution of intelligence in the universe. Unprecedented observational data will be available in the coming months to test these competing hypotheses based on objective facts. The tools are ready, coordination protocols are set, and the scientific community awaits results that could change our understanding of planet formation, the distribution of life in space, or humanity's place in potentially vast networks of galactic intelligence. If the Object 3I in Atlas ultimately turns out to be a natural comet with unusual chemistry, which, according to current data, is the most likely outcome, the scientific implications will significantly surpass simple classification tasks. We will need to fundamentally rethink our understanding of the diversity of comets, the chemistry of the outer star system, and the statistics of populations that regulate the distribution of interstellar objects in our galaxy. The dominance of carbon dioxide, early water activity, exotic properties of dust, and characteristic chemical signatures will create new categories within the taxonomy systems of comets developed based on examples from the solar system. This expanded classification structure will better prepare us for the chemical diversity expected from objects formed around various stellar masses, metallic compositions, and evolutionary histories. Models of the chemistry of the external system will require significant revisions to account for the formation conditions necessary to achieve unusual ratios of volatile substances and dust characteristics inherent to 3I Atlas. Specific parameters of the stellar environment that contribute to the formation of carbon dioxide-rich comets will be useful for theoretical models of planetary system formation in various galactic contexts. Population models of interstellar objects will receive important constraints through detailed analysis of a well-characterized example, observed at various stages of its passage through the solar system. The size distribution, chemical diversity, and activity level statistics derived from data on 3I and Atlas will enhance estimates of the overall density of interstellar objects and the frequency of their collisions with planetary systems. These refined population models directly influence the theory of planet formation, quantitatively assessing the resources available for seeding processes on cosmic timescales. Higher population densities will strengthen arguments for material exchange between star systems, while lower densities may support scenarios of more isolated planet formation. If the hypothesis about the seed of the planet gains support, whether through the example of the three-dimensional atlas or broader studies of populations, the consequences for planet formation theory could be revolutionary. Compelling evidence of the capture and seeding of Falsner will establish a completely new paradigm for the rapid formation of cores, explaining the observed correlations between star mass and the frequency of giant planet occurrence. This natural mechanism of seeding will solve the timing issue that has troubled traditional core accretion theory for decades. The ability to bypass the slow stages of dust and planetesimal growth through the import of ready-made cores will allow the formation of giant planets within the lifetimes of gas disks around stars of all masses. The theoretical foundation will also explain the chemical diversity observed in the atmospheres of exoplanets and their overall composition. Imported cores with chemical signatures from various star-forming environments will produce planetary compositions that exceed the range achievable through local formation processes. The hypothesis of seeding makes specific predictions about the architecture of planetary systems, which can be tested through the coordination of data on membership in star clusters with surveys of exoplanets. Dense and massive star clusters should demonstrate increased efficiency in forming giant planets compared to isolated star-forming environments. The programmatic consequences of any confirmed artificial origin will significantly exceed all results of natural sciences due to their impact on planetary defense strategies, research priorities, and international space political frameworks. The first confirmed extraterrestrial technology will be the most important discovery in human history. Planetary protection protocols will require immediate and thorough revision to account for potential threats or benefits from artificial interstellar objects. Current methods of diverting asteroids and comets assume natural objects following predictable gravitational paths, assumptions that will become invalid for maneuverable artificial systems. The search for extraterrestrial intelligence will shift the focus from passive radio telescope surveys to active monitoring of anomalous objects in our solar system. The possibility that alien technologies regularly traverse star systems revolutionizes detection strategies and contact protocols. International space policy will face unprecedented challenges in developing appropriate responses to confirmed artificial visitors. Questions of territorial jurisdiction, access rights to research, potential attempts at communication, and threat assessment will require entirely new diplomatic and legal frameworks. This discovery will also prompt the urgent development of specialized methods for intercepting interstellar objects based on technologies similar to the European Space Agency's comet interceptor concept. Pre-positioned resources in deep space can ensure rapid response to newly discovered interstellar objects, providing close-up analysis opportunities that cannot be achieved through remote observation alone. Launch systems on Mars could become optimal platforms for interception due to lower gravitational overcoming requirements and favorable orbital mechanics for achieving interstellar trajectories. The development of such capabilities will be a natural progression of the current Mars research infrastructure towards the active study of interstellar objects. The data culture arising from the Triclops research of Atlas transcends specific scientific discoveries, enhancing the coordination methods of international observational campaigns and the analysis of archival data. The coordination protocols developed for this campaign serve as templates for future multi-resource observation programs involving several space agencies. The success of archival restoration using data from surveys like Atlas, Wiki Transient Facility, and satellites for exoplanet research demonstrated the value of maintaining extensive databases of astronomical observations. These archival searches expand the time frames of observations and provide important constraints for determining the trajectories and evolution of object activity. Rapid international coordination achieved in the observations of the three-eyed Atlas sets a precedent for responding to future discoveries requiring urgent observational campaigns. Communication protocols, agreements on data sharing, and mission planning procedures developed during this campaign will be useful for future research on interstellar objects. The collaboration between the European Space Agency and NASA in the observation phase of Mars demonstrates the possibility of resource coordination among different space agencies to achieve scientific goals. This model of cooperation can be applied in other contexts requiring rapid response and international resource exchange. Philosophical consequences extend beyond technical questions about planet formation or the discovery of life, touching on fundamental issues about humanity's cosmic context and our connection to potentially vast networks of galactic intelligence or biological distribution. The processes of natural seeding can change our understanding of planetary systems, viewing them not as isolated events of formation, but as collaborative creations with chemical contributions from various corners of the galaxy and time. Earth's materials may include components originally formed around stars that completed their life cycles before our sun began nuclear fusion. This perspective of galactic blending erases the boundaries between local and alien chemistry, establishing complex hereditary ties between worlds separated by vast distances and timescales. Planetary systems become nodes in cosmic recycling, networks that function over geological timespans. Biological seeding scenarios could establish the distribution of life as a cosmic phenomenon, not limited to planets. This will have a profound impact on astrobiology research, life detection strategies, and our understanding of biological evolution, transcending existing scientific paradigms. Artificial origins of life will present humanity with evidence of an intelligence operating on scales and timeframes beyond the capabilities of human technologies. This discovery will both humble us with our technological achievements and inspire us to expand our understanding of what intelligence can achieve over cosmic timespans. The reaction to confirmed artificial visits will be a test of humanity's ability for unified action, thoughtful analysis, and caution when facing potentially superior technologies. This discovery could serve as a catalyst for unprecedented international cooperation or exacerbate existing tensions between states competing for access and benefit. However, besides the political consequences and scientific discoveries, the study of the three-dimensional map of the eye has already demonstrated humanity's remarkable ability for coordinated curiosity, thoughtful analysis, and openness to unusual possibilities, while maintaining strict standards of evidence evaluation. The process itself, regardless of the final conclusions about the nature of objects, illustrates the ability of science to transform apparent anomalies into deeper understanding through patient observation, theoretical creativity, and collaborative research spanning various disciplines and international borders. Thus, broader stakes go beyond any single discovery and encompass the development of human knowledge, international cooperation, and our species' ability to confront cosmic mysteries that challenge fundamental notions of our place in the universe. The question of whether star systems exist as isolated islands of chemistry or participate in vast galactic networks of gardening touches on the deepest foundations of our understanding of cosmic ecology and our place within it. If interstellar objects regularly transport materials, organic matter, or even life between star systems, the boundaries defining separate worlds begin to blur, transforming into shared creations spanning light years and geological epochs. This cosmic ecological perspective transforms our understanding of planetary identity from disparate entities to nodes in an interconnected network of chemical and potentially biological exchange. The atmosphere, oceans, and living systems of Earth may include materials originally formed during the existence of stars that died billions of years before our sun began nuclear fusion. The consequences of this go beyond academic astronomy and touch on fundamental questions of origin, legacy, and responsibility that affect creation narratives in every human culture. If worlds are formed through galactic cooperation rather than in isolation, the concept of home expands to encompass the contributions of countless star brothers throughout cosmic history. The modesty of origin may become the deepest philosophical consequence of cosmic seeding processes. The assumption that planetary systems are independent achievements of local physics and chemistry dissolves in the recognition that worlds can be co-created with the galaxy through mechanisms operating on scales beyond human understanding. This perspective places Earth in a cosmic community of mutual dependence and shared heritage, expanding our notion of kinship beyond biological boundaries towards geological and astronomical relationships. We become not just products of earthly evolution, but participants in galactic processes that connect our world with star-forming regions thousands of light years away. The question of what is alive and what is lifelike becomes more complex when considering the possibility that the three eyes of the Atlas may contain biological materials, biotechnological systems, or autonomous technologies that blur traditional categories. Definitions separating living organisms from complex machines are becoming increasingly arbitrary as technology approaches biological complexity. Current research in synthetic biology, programmable materials, and artificial life is already questioning the traditional boundaries between biological and technological systems. Materials that grow, reproduce, adapt, and respond to environmental changes can possess all the functional characteristics of life while remaining fundamentally artificial. Applied to interstellar exploration scenarios, such hybrid systems can provide amazing capabilities for adaptation, repair, and mission flexibility in unpredictable circumstances encountered during million-year journeys between stars. The distinction between biological and technological becomes less important than the functional requirements for survival and operation. If the three eyes of the Atlas truly contain such systems, which are currently unsupported by evidence, this will be our first encounter with technologies that transcend human conceptual categories for classifying natural and artificial phenomena. This discovery will require an expansion of philosophical frameworks to understand intelligence, life, and their interconnection. The paradox of the Great Silence, the apparent absence of detectable extraterrestrial intelligence despite the vastness and age of our galaxy, may find resolution through the dark forest concept. Hypotheses suggesting that highly advanced civilizations exercise extreme caution in revealing their existence or capabilities to potentially hostile species. This interpretation suggests that survival in a competitive space environment may require complex methods of camouflage, deception, or distraction, making alien technologies nearly indistinguishable from natural phenomena. Advanced civilizations can regularly observe younger species while remaining completely unnoticed due to their superior camouflage equipment. The consequences for human behavior and communication ethics become complex when it comes to whether to initiate communication or maintain defensive silence upon confirming the discovery of concealed alien technology. The choice of response may have a decisive impact on the survival of our species if the dark forest hypothesis accurately describes the galactic power structures. On the other hand, the apparent cosmic silence may reflect communication methods, energy scales, or conceptual frameworks that surpass current human technological and intellectual capabilities. What seems like absence may actually represent a pervasive presence acting through mechanisms we cannot recognize. The philosophical question of wisdom versus openness takes on existential significance in the context of possible evidence for the existence of extraterrestrial intelligence or technologies. The decision to actively pursue contact or maintain cautious observation could affect the long-term survival and development of humanity in a potentially populous galactic community. Current protocols assume benevolent or at least neutral intentions from potential extraterrestrial civilizations, but this assumption may prove catastrophically naive if competitive or hostile intelligences dominate galactic power structures. The discovery of camouflaged reconnaissance technology will indicate much more complex and potentially dangerous scenarios. Human narrative structures built on assumptions of cosmic isolation will undergo fundamental revision if objects like the three-eyed atlas serve as evidence of widespread intelligence or biological diversity across the galaxy. Cultural, religious, and philosophical systems must consider humanity's position as one of potentially millions of intelligent species. The significance of human achievements, uniqueness, and cosmic importance will require rethinking in contexts where intelligence and life may be commonplace rather than rare. This transition can be both humbling and inspiring, depending on how our kind chooses to interpret expanded membership in the cosmic community. Nevertheless, the philosophical implications go beyond simple scenarios of discoveries and raise questions about curiosity, exploration, methodology, and the right balance between skepticism and openness when faced with phenomena that challenge established understanding. The study of the three-eyed atlas demonstrates humanity's remarkable ability to simultaneously adhere to strict scientific standards while remaining genuinely open to revolutionary possibilities. This intellectual balance is one of the most valuable abilities of our species to explore cosmic mysteries that go beyond current knowledge. The process of investigation, regardless of the final conclusions about the nature of the object, demonstrates the philosophical values of collaborative search based on evidence of reasoning and careful distinction between speculation and justified facts. These methodological approaches provide a solid foundation for encountering even more astonishing discoveries that may await us. The philosophical dimension also encompasses issues of responsibility and governance arising from an expanded awareness of cosmic interconnectedness. If worlds across the galaxy participate in networks of material exchange or targeted seeding processes, humanity may bear the obligation to continue such actions or protect them from destruction. The acknowledgement that the chemical and potentially biological heritage of Earth extends to galactic scales creates ethical frameworks that go beyond traditional concepts of environmental protection and lead to cosmic ecological responsibility. Our actions can influence not only terrestrial ecosystems but also processes of galactic scale that operate over geological timescales. These expanded concepts of responsibility challenge anthropocentric views of the world, while providing inspiring visions of humanity's potential contributions to cosmic evolution and development. Instead of being isolated observers of cosmic phenomena, we can become active participants in the galactic processes that shape planetary formation and the distribution of life. A philosophical journey initiated by the exploration of an object called triangular atlas thus extends far beyond questions about this specific object to a fundamental inquiry into the cosmic context of humanity, our methods of understanding reality, and our commitments within potentially vast networks of mind and life spanning our galaxy. The process of research demonstrates that the greatest value of science may lie not only in answering specific questions, but also in expanding our ability to ask better questions while maintaining both rigorous skepticism and genuine openness to possibilities beyond current understanding. As we approach the final assessment of the evidence and competing hypotheses, these philosophical considerations provide important context for understanding the stakes involved in determining the true nature and origin of the triangular atlas. Part 3. Concluding Reflections. Three roads diverge in a cosmic forest, each leading to profoundly different consequences for humanity's understanding of its place in the vast evolutionary processes of the galaxy. The evidence gathered over months of unprecedented observations now allows us to assess which path best explains the mysterious visitor we have come to know as the Triangular Atlas. The interpretation of the comet is an astronomical object with three eyes, an unusually chemical yet natural phenomenon that expands our understanding of the diversity of interstellar visitors while remaining within the established laws of physics. This scenario will establish the object as scientifically significant, without the need for revolutionary revisions of our understanding of life, intelligence, or cosmic ecology. The predominance of carbon dioxide, early water activity, exotic dust properties, and characteristic signatures of polar images will create new categories in comet classification systems, while showcasing the chemical diversity achieved from formation around various stellar masses and evolutionary histories. The scientific value will be significant due to improved models of interstellar object populations and a deeper understanding of the chemistry of external stellar systems. The interpretation of the artifact, though lacking supporting evidence in current observations, could become the greatest discovery in history if confirmed by technologies that leave clear traces. This scenario requires exceptional evidence that current measurements have not provided, but its consequences will instantly change all aspects of human civilization. Confirmed extraterrestrial technology could revolutionize planetary defense strategies, extraterrestrial intelligence research, scientific research priorities, international space policies, and the philosophical understanding of intelligence distribution in the cosmos. The discovery will simultaneously humble the achievements of human technology and inspire expanded notions of what intelligence can achieve on galactic timescales. The interpretation of the planet's seed offers a natural mechanism for exchanging cosmic material that could revolutionize the theory of planet formation without the need for biological or technological explanations. This scenario provides elegant solutions to the timeline problems tormenting traditional core accretion models, explaining the observed correlations between star mass and the frequency of giant planet occurrence. The concept of the seed suggests that planetary systems develop through galactic cooperation rather than isolated formation processes, transforming our understanding of worlds from independent entities to nodes in vast recycling networks operating on geological timescales. This natural explanation carries revolutionary consequences while remaining fully within established physical principles. The uncertainty inherent in our current knowledge reflects the real time of scientific discovery, unfolding through careful observation and analysis. The meeting with Mars on October 3rd, the perihelion passage on October 29th, updated observations of Earth in December, and the approach to Jupiter on March 16th may provide crucial evidence needed for final classification. Each upcoming observational event offers specific opportunities to test competing hypotheses. High-quality imaging from Mars may reveal jet structures, indicating natural gas emissions or artificial control systems. Monitoring near perihelion can reveal reactions to extreme heating that help distinguish biological, technological, or purely physical processes. Spectroscopy after perihelion can document chemical evolutionary patterns that separate natural volatile processes from controlled emission sequences. A meeting with Jupiter will provide ultimate tests through experiments in gravitational physics and the effects of high radiation conditions that could trigger reactions from hypothetical biological or technological components remaining dormant under normal interstellar conditions. The combined data from all stages of observations will help determine which interpretation best matches the collected data. We urge you to monitor the upcoming data releases from NASA and the European Space Agency, paying attention to specific diagnostic signatures that may distinguish competing explanations. isotopic ratios indicating exotic formation conditions, non-gravitational accelerations suggesting artificial propulsion, or complex organic signatures hinting at biological payloads will become crucial evidence for assessing unusual claims. The scientific process demonstrates its greatest strength in its readiness to follow evidence wherever it leads, while maintaining high standards for unusual discoveries. The study of the 3I Atlas project exemplifies the balance between sincere openness to revolutionary possibilities and strict skepticism that protects against premature conclusions. However, aside from technical questions about classification and origin, the 3I Atlas has already expanded human perception of the possibilities hidden in cosmic phenomena that initially seem ordinary. The process of research shows that science can transform obvious anomalies into deeper understanding through collaborative investigation spanning multiple disciplines and international borders. Philosophical implications extend beyond any specific discoveries and encompass fundamental questions about cosmic interconnectedness, material exchanges between worlds, and humanity's place in potentially vast networks of galactic evolution, whether natural, artificial, or something in between. The 3I Atlas has already challenged assumptions about isolation, uniqueness, and the boundaries defining separate planetary systems. We conclude our research with a thought experiment. What discovery will have the greatest impact on the future development of humanity and our cosmic understanding? Will the awareness that we exist in a galaxy where worlds are regularly seeded by natural processes change our perception of our planet's heritage and our obligations to continue cosmic gardening? Activity that confirms the observation of extraterrestrial intelligence will require an immediate reassessment of all assumptions about human uniqueness, cosmic isolation, and the necessary balance between openness and caution when encountering higher technology. We discover that nature operates through mechanisms that are much stranger and more interconnected than modern theories predict, inspiring the advancement of human knowledge and technological capabilities. Every potential answer carries deep consequences for the trajectory of civilizations, the priorities of scientific research, and the philosophical foundations that guide our understanding of meaning, purpose, and responsibility in a cosmic context that transcends the boundaries of individual planets. The proposed voting opportunity reflects the democratic nature of science, acknowledging that data interpretation ultimately depends on human judgment, community assessment, and the collective wisdom arising from open dialogue among various viewpoints and areas of expertise. We promise to continue highlighting key data obtained from observations of Mars, perihelion monitoring, post-perihelion spectroscopy, and analysis of the encounter with Jupiter. The scientific story continues to unfold as evidence accumulates during the largest study of interstellar objects ever undertaken by human technology and international cooperation. The comments section becomes a forum for discussing data interpretation, assessing competing hypotheses, and exploring philosophical implications that extend beyond technical classification and touch on fundamental questions about humanity's cosmic context and our relationships with potentially vast networks of galactic intelligence or biological distribution. Whatever ultimately exists in the 3-eyed Atlas, a natural comet, an artificial probe, a biological courier, or planet seeds, it has already demonstrated the universe's ability to present phenomena that exceed our current understanding, prompting us to develop better questions, improved research methods, and expanded conceptual frameworks. This object serves as a reminder that cosmic mysteries await discovery in the spiral arms of our galaxy, in stellar nurseries and interstellar spaces, where wanderers roam between encounters with fate that can change entire civilizations and their understanding of their place in the cosmic evolutionary process. The exploration continues as the 3-eyed Atlas moves towards its meeting with Mars, then the Sun, and then Jupiter, carrying within its core secrets that first formed around alien stars in the distant epochs of galactic history. Answers await those who are patient enough to follow the evidence, remaining open to possibilities that transcend current human knowledge and imagination. The universe still seems to hold surprises for those willing to carefully observe the visitors from the space between the stars.